All right, yeah, good morning. Thanks for coming. That's the agenda for today. This is a picture from my beautiful hometown of Berlin, an old NSA listening station. So I'm going to start with the introduction. And I think this is an important and famous quote to remember, especially when you're looking at sales prospects from various vendors and so on and so forth. Trying to define or give a definition of AI is really hard because intelligence is hard to define in the first place. I mean, there's been like centuries of philosophy, cognitive science, I don't know what, theology even trying to define intelligence, and there's no definition that really applies across all fields. It's also constantly shifting.
Come on down to the front. The seat's down the front for sure. Don't feel you've got to lurk at the back.
Yeah, I even brushed my teeth this morning, so it should be fine. Interdisciplinary. And if you look at the computer science field that deals with AI, there's been various approaches as well. So cybernetic, trying to imitate the brain, more logic-based approaches, more probabilistic approaches. So there's not even unity within one field of science. Nevertheless, I'll give it a try. I could say that a machine that somehow is able to make perception, perceives its environment, and then takes actions which somehow optimize or maximize a success for a certain or a given goal, could be called artificial intelligence. And then basically this machine would carry out functions or imitate functions, that's an important distinction, that we as humans would attribute to the human mind or human cognition or whatever you want to call it. So some examples of these functions would be decision making, problem solving, or learning. There's some categories in the space which have evolved over the years. So you can talk about weak, narrow, or domain-specific artificial intelligence, and that basically means it can perform a very specific task as well, or even a little bit better than, or much better than humans. And some of the expert systems we already saw in the 1980s, and some of the machine learning and deep learning powered approaches currently achieve narrow AI successes. There's another thing called strong or general AI, which is a bit more. That would basically mean that it can perform any intellectual tasks that humans can. Well, depending, I should probably define which humans, but that's another story, I guess. And such a thing doesn't exist yet. I think that's always important because a lot of people are always talking about AI, and technically speaking, they're always referring to weak AI and not general AI. And the science fiction stuff is usually general AI. And then if part 2 came to happen, it would probably lead to something like super intelligence, but that's then getting into the futuristic space, at the moment at least. Why it's not working? Yeah, so that's a Canadian, so I'm not responsible for that. But he's one of the most important researchers in the field, so probably knows what he's talking about. This is a thing called periodic table of AI. All the sources of this are in the presentation, so later on you can download it and click on them and follow up. And you can also, it's on a website, so you can click on each of these functions and deep dive if you want to learn more. But it illustrates how many different functions need to be realized if you really want to have a complete AI instance. And you can broadly group them into assessment, inference, and response functions. Some of them are relatively famous. I mean, stuff like face recognition I know Google Picasa, Google Photos does it, and if you cross a border, usually some system will be in place to identify the face even. Translation is somewhere there as well, speech recognition. So these are all functions, and depending on what you want to achieve, you need a different approach. Before I come to the actual methods that are being used to achieve successes in this field, I wanted to give you just a very brief history, because it's actually quite important to see how the field has evolved. This looked different when I did it on my computer, but never mind. So actually the theory behind the current hype thing, neural networks, is actually from the 1940s. So, I mean, not the complete theory, but the first paper in this field. And AI itself as a scientific discipline, as a scientific field, was established in 1956. There was a lot of excitement. Some quotes from the early 60s that the problem would be solved within a couple of years. Just around the corner, yeah. Probably a bit too optimistic. And that was actually the problem, because in the late 60s, early 70s, funding was more or less completely pulled from the field, and this led to something called the first AI winter. So if you were an academic and you had AI on your resume, or were basically openly stating that you're conducting AI research, that would not have been too beneficial for your career. And then they created different labels around it. Computational linguistics was one, and some others. In the 80s, early 80s, there was a thing called the knowledge revolution. That sounds really great. Made a short comeback because there were some expert systems around that achieved successes in a very specific domain, subject domain. But then again, basically by the end of the 80s, it was clear that these systems wouldn't scale and wouldn't be applicable to a wide range of topics just like that. So basically, the second AI winter hit, and it lasted until quite recently. I just included this because David is always talking about his dragon computer back in the days. He's telling the war stories. So like end of the 90s, a company called Google started to appear on the scene. We had stuff like semantic web happening. We had big data as a hype thing a couple of years ago. Everybody still remembers it, I guess, more or less fondly. And then basically the current big thing is deep learning. And again, an important takeaway is the theory behind it is not really new. This slide from another conference sums it up quite nicely. What's new since the 80s? Basically more data, faster computers. That's not quite all of it, but I think the last point is really important. There's also more funding these days. So like the big guys like Google, for example, they decided to invest heavily into this field. And of course, like defense, intelligence agencies spend quite a lot of money on it as well. And I don't know what the future will bring, but hopefully not quite as dark. I like the picture. So to sum it up, what we saw in the last 15, 20 years is, you could call it an evolution of methods or shift in importance. So 1996 was the famous Deep Blue thing. That was IBM, right?
Yeah. It was IBM.
The program that beat the chess grandmaster. And that was a rule-based system. 2016 was the Google thing, DeepMind, camel case. And that was the thing that beat the Go champion, or has just recently beaten another bunch of Go players. And that was not a rule-based system, but was a deep learning-based system, basically trained itself on a very, very large data set. They actually used, they had like an online, you could play Go online, and players were playing it, and the network was sitting behind it and learning from all these players who were thinking they were playing against, I don't know, a very shitty human opponent, until it got better and better. Sneaky. And I think it's also important to not believe the hype too much, because I think we've seen it in this short history that there's been a lot of excitement and then a letdown, and also with all the semantics and big data we've seen in the last 10 years. So if you are looking at vendors or solutions or services out there, sometimes it's not really AI powered, because it just looks neat, right? But you could achieve the same result if you sat down over the weekend and I don't know, got involved with your Excel or whatever application. On the other hand, the reverse is also true, that once something has been implemented, is out there, people don't really recognize it as AI anymore. It's commoditized, it's been solved. So the last quote, I think, sums it up quite nicely. So once it has been automated, can't be that difficult, right? Because it's been automated. So it's not intelligent anymore. But if you took, like, I don't know, the current Google Maps app and showed that to someone from the 80s or 70s, they would probably say it's highly intelligent, right? I mean, it does, it knows in real time the public transport, the amount of traffic on the Mass Pike, and can tell you the optimized routing to your destination, and knows like which restaurants are open and how they've been rated. And that would probably look like magic, but for us, yeah, of course, it's pulling these data sources, it's pulling this data in, it's relatively easy to do, right? So, so that's the goalposts are constantly shifting. So it's really also very hard for the people working in this field to get proper recognition, because once it's out there, it's already yesterday's news. What we're also seeing is that a conflation of terminology. So people are talking about AI all the time when they really are talking about machine learning maybe, or some other method in this field. So a lot of the solutions we have maybe seen and heard over the last 1.5 or 2 days are actually not AI powered, but more precise term would be machine learning powered or based. There's, broadly speaking, two categories of methods, and one of them can be called symbolic and the other sub-symbolic. These are the terms that have been established, I think, over the last couple of years. And machine learning is one of the sub-symbolic methods, whereas the rule-based approaches we've known for many, many years are more in the symbolic category. And deep learning is a subset of machine learning. So that's just to get the picture clear. And what's so special about it? This is the symbolic stuff. I just labeled it a classical approach. This is probably more or less well known to most people. The important takeaway is you need human expert knowledge, and you need to encode this in data and rules. So it acquires, it doesn't scale too well, right? But on the other hand, when it's done right, it yields good results, and it has a high degree of explanatory power. So you know why the system actually does what it does, or you know if you know the details. And you don't necessarily need a gigantic data set. The new stuff is different, and not everybody is happy with it, like the two quotations in brackets. The last one, glorified weather forecast, is from Noam Chomsky, so he's not a big fan of these approaches. And there's an interesting online debate between a couple of these guys, so if you want to take a closer look. I recommend it. It's quite funny at times. But here the important takeaway is they really need large data sets, these machine learning approaches. And I was talking to a colleague from Elsevier a bit earlier today, and so like when some publishers approach me and ask me how can we use a machine learning approach, and sometimes you actually have to tell them, well, the data set you're looking at is not big enough. So it's not maybe not the right approach for you, or you need to find ways to extend your data set. You also need quite a lot of computing power, and also sometimes some special hardware. And you still need to perform some work. It's not like you just upload a data set somewhere and things magically happen and there's an output. You still need people to assess the quality of the results and to prepare the data set. Also make sure it's not biased, as we saw with the Microsoft thingy.
The racist.
The racist bot. And I think the most famous example of a transition from symbolic to sub-symbolic was in machine translation, what Google basically did last year, where they had huge gains in the quality of translation of translated texts. But this approach suffers, and that's the point that Chomsky is also making from a black box problem. You see the input, you see the output, but you don't know why the network has arrived at this output, which for some people is not important as long as the output is good, but some people actually would like to know why. So, yeah, deep learning, as I said, is a subcategory, a subfield of machine learning. What we're seeing these days is so-called artificial neural networks, and to be more precise, multi-layered artificial neural networks. Nobody can say that, so it's usually ANN. And again, like this is really important. You need a lot of power to do this because it's all been around since the 1980s. Back then, people just didn't have the data and didn't have the computing power to do it. And now Google just built their own chip, their own hardware design, a chip that is optimized for parallel processing, specifically for neural network related processing. So that shows that even today the existing hardware wasn't good enough for them. And there's some interesting links there if you want to follow up on the details. Need to speed up. I'm going to go over these details because we don't have enough time, and I don't want to steal David's time, but it's on the slides, and you can take a look at the 3 different types of learning that are out there, but it's probably will be too much detail for right now. Just wanted to quickly illustrate how such a network actually works. I mean, it's to explain it in detail, we would need a 2-day seminar, and we would actually need some formulas, so I'm avoiding formulas today. But it's basically you have an input, you have a number of layers in your network, which then leads to an output. Sounds great, right? So basically one example could be facial recognition, where the first layer just recognizes whether there's an edge or not. So pixel versus no pixel, very simple. And I mean, there's not just 3 layers, so there would be like 3,000 maybe, or 300. And each higher layer is looking for patterns in the lower layer. So the second layer would look for patterns of edges, and then might come to a conclusion, oh, it's a circle or it's a rectangle. And so on and so forth until the last layer would determine, oh yeah, this is a face, so more or less abstract representation. And there's more behind it. They would also propagate back into the lower layers if they found errors, but that's then really mathematics and a bit more complicated. Another example to illustrate this is building a robot. Unfortunately, not Optimus Prime, because that would be really cool. And the examples are taken from this super excellent introduction. So if you want to follow up on this, It's also in the references to this slide. It's under a CC license, freely available, great read, and some parts of it are even non-technical. So if you imagine you want to build a robot, very simple robot, 2 motors, 8 sensors, like 2 in the back and 6 in the front, and it can do nothing else but drive or stop. So no changes of direction, no nothing. Classical approach would be you go ahead, basically you need to map the input values to the output values. I mean, there's sensor data coming in, and you need to map that or translate it into instructions for the motor to either drive or stop. And you would probably write a program, or if you're a real nerd, design your own circuit board, and then encode the knowledge about each of these values and states into actions for the motor. Shouldn't be too difficult for such a simple example. The machine learning approach would be you create a training sample. So basically you have a bunch of input data and you label them, each of these input data sets or input data data sets as good or bad, or move or stop, the desired output. And then you feed it to your neural network, which is a black box. It doesn't have explanatory power. There's a learning algorithm in this net that teaches it to this network, and it then generalizes from the samples and finds a universal rule. When do I have to stop and when can I go? But you don't have to teach it every possible sensor input combination up front. Let's skip over this. So the difference would be if you just make a very short or slight change. So if you just make the change that the 2 motors can move independently, which would allow it to change direction, the first approach would already be hugely more complicated because you need lots and lots more rules to encode, whereas the second approach probably would be more suitable to such a problem. To wrap up, the interesting thing, it's relatively new, but we're also seeing already a commoditization, I think is the English word for it, and maturation in this field. So you have all the usual suspects, all the big companies, some not so big companies, offering really as a service solutions in this field. So you can hook up with AT&T Speech or I don't know, Amazon Lex, Microsoft Lewis, if you want to actually build certain pieces and you don't have to code and come up with the learning algorithms and all the neural network programming on your own. The important thing is who owns the data, who owns the IP, and who owns the results. So that should be important. Like I think the Microsoft thing, they actually let you take away all the data that has been generated. So you could, in theory, move it somewhere else, whereas other approaches are probably more vendor lock-in. And the biggest funder is still the government and the military. Also shouldn't forget that. Some real-world examples to finish it off. I mean, all the big players, of course, you all know them, and they're doing a lot in this field. Some from outside our industry. John Paul is like a AI-powered concierge service. Cogito does marketing services. Science itself is using deep learning techniques more and more. So especially the data-rich sciences. There's a nice blog post by O'Reilly about this, if you want more details. Climate science doesn't exist here, so I struck it from the chart.
It is roots.
I'm from Europe, so we have climate science. And what is quite obvious is, of course, like mining of scientific literature, right? I mean, that's that's the first application that comes to everybody's mind. There's a number of startups and not so startup-ish anymore around claiming to provide solutions here. Time will tell, I guess. Some of them are extremely well funded now. So another thing is around the whole peer review thing. I mean, plagiarism check today is string comparison more or less, right? There could be more intelligent solutions to that, or curating data, data sets, research data. And then, of course, the usual other well-funded fields of industry like healthcare, finance, and also in education has already seen intelligent tutor systems in the field. And translation. So, to wrap it up, beware of the snake oil salesman. I think a lot of publishers have purchased semantic solutions in the last 10 years and not been entirely happy about the return on investment. But some important takeaways, I think the world is not a data set. So no matter how big the data set is, so you never have a complete representation of the real world. If some new solution says it's using advanced technology to super duper whatever, then you should probably ask for either patents filed or references to scientific articles to actually prove that claim. Make sure you know how much training data you need to use this new tool or service, and if this training data set actually exists yet, or whether you need to spend another 200K to create it first or curate it first. Can it work unsupervised? And how much human intervention does it need? And over which time frame? And then again, who owns the outcome, the input, and what happens in between? And so, without further ado, I give you the evil overlord.